We can definitely see your first slide. I mean,
okay, I see. Excellent. All right, thank you. Yes, so I'm a software scientist at the Molecular Sciences Software Institute. We are a US-based and NSF-funded organization designed to support the development of software within the computational molecular sciences community. And one of our primary concerns is that of interoperability. Now, of course, this is a very broad term that can be used in many different ways. So I would distinguish between a couple of different approaches to interoperability, one of which being ex vivo interoperability. That is to say, cases in which you want codes to interoperate, but you don't necessarily need both codes to be live at the point when they're communicating. So you might have a case where, for example, you have one code that writes an input file that's then read by another code that runs to completion, writes its output, and then that gets read back in by either the same code or maybe by an entirely different code in a sort of workflow format. Now, this is a type of interoperability that we're very much concerned with at the MOISSI, and we've developed the QC Engine project in this area. This is a Python-based program executor and I/O standardizer. And what I mean by that is it enables you to write a standardized Python script that contains input that can be that can then be used by a number of different participating codes, and more codes are being added over time. And then it enables parsing the output from those codes in a standardized schema. Another approach to interoperability is that want codes to be able to interoperate while both codes remain live. This is something that you would be concerned about in scenarios where maybe the intrinsic message latency associated with ex vivo communication is a problem, or maybe you need a finer level of communication between codes and finer level of control than what you could achieve through ex vivo communication. And to this end, I am leading the MOISSI driver interface project. And this project is designed to provide a standardized API for this sort of fast, on-the-fly, in vivo type communication. And in particular, we're working with this project to support codes that interoperate in a driver engine paradigm. So this would be something along the lines of a client-server model, where you have a client-like driver that sends commands or requests, if you will, to a server, one or more server-like engines that then respond to those commands in appropriate ways. And there are a number of codes within the community that have adopted this sort of paradigm to great success, among them things like Kimshell, IPy, Sages, PlumD, etc. And what we're trying to do with this project is to support these types of development efforts and to simplify the process, in particular, of interoperating codes in this in vivo context. And so the MDI project consists of two distinct components. We have, on the one hand, the MDI standard, which is an API-like definition of a command set that can be sent from drivers to engines. And this command set includes various basic tasks like sending and receiving coordinates, forces, energies, etc., etc. We also have commands that allow a driver to control elements of the high-level program flow of the engine, so commands that, for example, let you start an MD simulation and step through different components of each time step of that MD simulation. And then we have the MDI library, which handles the actual technical details of sending and receiving bytes between codes. And the MDI library currently supports communication via MPI and TCP IP sockets. We also have some early implementation of support for using the MDI library to communicate between codes and linked libraries. So that essentially just allows you to use the standardized interface in all of these different scenarios. And it's designed to support a variety of different languages as well as software platforms. So just by way of clarifying a little bit of what we want to be able to do with MDI, I have here, and I apologize, the slides are sort of doing their own thing here. But I have this example of a simple 50-line Python script that implements an ab initio MD driver. So the idea here is I'm writing a driver that takes two codes, a QM code and an MM code, and it's going to use the QM code to compute forces and the MM code to actually do the MD time steps, to do the time integration steps. And so what we're going to be doing here is, first of all, using MDI to establish a connection between a QM and MM code. And then we'll actually start using the MDI standard to send commands to the engines that they'll then respond to. So for example, right here, we're using MDI, the MDI library, to send a command, this command that says, send me your number of atoms, to the MM code. And then we can just use an MDI function, MDI receive, which is very much analogous to MPI receive, that is going to accept the expected one integer from the MM engine. And then we can send additional commands in order to handle the rest of the processes necessary for this AIMD driver. We can send a command that tells the MM code, initialize an MD simulation. And so the MM code will initialize that simulation, but it won't do anything else. It'll just wait for further commands. And then we have an iterative loop where every iteration of the loop, we tell the MM code, go to the next point in this MD simulation where you evaluate forces, and then stop there. And work, which is to say, okay, send me your coordinates, and then we shuttle those over to the QM engine. We request forces from the QM engine and send them right back to the MM engine. So we've replaced the MM forces with the QM forces, and we've written this driver that allows us to run ab initio MD even if our underlying QM code doesn't have an MD implementation. Now, one of the really nice things about this is that you can then build lots of additional, more complex and more interesting types of drivers on top of this. So we've been working on the development of a few proof of concept drivers. These are fairly bare bones implementations that are really intended just to be able to support other developers as they work towards developing more fully featured drivers. But we've written basic implementations of AIMD, QMMM, nudged elastic band drivers, metadynamics drivers. In particular, I'll call attention to the nudged elastic band driver, which is especially interesting in this context, I think, because what we did with it is we wrote it in such a way that each nudged elastic band image can be performed by a different instance of the engine. So in other words, we've written this in such a way that it implements a higher level of parallelization than necessarily exists within the underlying engine. So we can write just through Python and MDI higher levels of parallelization and higher level techniques that exist on top of the underlying engines. We have direct support for a number of different engines, as well as QC engine, which essentially means any code that works with QC engine you can also control with an MDI driver. Although that would entail working within the ex vivo context. Within the overall context of HPC, I do think there are a number of nice features of MDI. We've certainly designed it to be functional in that setting. So we have, as I showed you, designed the interface to be as MPI-like as possible and to support, in particular, communication via MPI. And as I showed with the levels of parallelization on top of whatever may exist already. I will say, this is all with a caveat, that currently data is communicated through rank 0 of any participating code. So in other words, if you're running these engines in parallel, there's an implied gather or scatter type operation. One of our ambitions is to work on removing that requirement so that data can be communicated between codes in a more distributed way. And so I'm hopeful that we'll have something that's really useful to the HPC community there. And then I'll just say that one of our priorities moving forward is to engage with the rest of the community and to work with people who are currently developing drivers or engines. So I would say, by all means, if you are currently working on a code that you believe could benefit from some sort of MDI integration, then please let me know. I'd be happy to assist in any way I can. Thank you.
Thank you for a very nice talk. If there are any questions for Taylor, please again use the chat line so that we can push on with the next talk. Volker, are you ready in the background? Oh, by the way, Taylor, you need to stop sharing so that we can move on. But again, thank you